In the previous session, we discussed how we deal with the standard normal table in order to find the area under the curve, under the normal curve, or the x values or z values corresponding to some area. Now we're going to move to some practical examples to see how we can make use of the applications or the tools we have so far in real world examples. So let's go for the session and see how we can actually use the area under the normal curve in getting useful information in real applications. First, we need to emphasize a few steps that one has to do or has to follow in order to use the standard normal curve or the standard normal table. As I mentioned in the previous session, it's always useful to sketch the normal curve associated with the variable to describe the problem in question. Step 2 is to shade the region of interest and mark its delimiting x values, so we will know what region or what area we are after. Step 3 is to calculate the z-scores corresponding to the x values using the transformation of z equal x minus mu divided by sigma, which we discussed in the previous sessions. 4 is to use the standard normal distribution table to find the area under the standard normal curve delimited by the z-score. So now we're moving from the x to the z. Finally, is to express the findings back into x values, as we will see by example. So 5 basic steps: sketch the normal distribution, shade the region of interest, calculate the z-score, use the standard normal distribution table to find the area, and then express your findings in terms of x. Let's see how these steps apply to any example that we deal with. Here is an example. According to the controversial 2002 book titled The IQ and the Wealth of Nations, the average IQ test score of the world was 88, and the standard deviation was 12. Now, in case you don't know, here are the common criteria that are used to describe people IQ. Anything below 70 is extremely low IQ. 70 to 79 is borderline. 80 to 89 is low average. 90 to 109 is average. 110 to 119 is high average. 120 to 129 is superior. And 130 or plus is very superior. Regardless whether we agree with these criteria or not, let's deal with the problem. The findings said that 88 is the average score of the IQ worldwide, and 12 is the standard deviation. Now, the question here is to determine the percent of people in the world that their intelligences are considered above average or better. That's IQ greater than or equal the 110. That's above average or better. The second question is to determine the percent of people in the world that their intelligence are or is considered average, meaning 90 to 109. Well, all what we have here is two parameters or values of two parameters, mu and sigma. So we have the average mu being 88 and the standard deviation sigma equal 12. And provided that we trust the values of these parameters, because that's the key issue, is to trust the values and make sure that these values are reliable, then we can use the features of the normal distribution and the transformation that we discussed before to answer any question associated with the data. So the first question determined the percent of people in the world that their intelligence is considered above average or better. Let's see that. Here is a normal distribution, and here is the average, and the standard deviation, as we know now, is 12. So at 110 or more, we can, after we sketch the normal distribution, which is the first step, we can kind of identify where is the 110 is going to be, say somewhere in here. So now we very much know where is the 110 by rough sketching of the normal distribution. We also know what area that's desired. That's the percent of greater than or equal 110. So we're talking about this shaded area here. So that's the first step. We sketch, we identify the values of x as specified by the problem or the question being addressed. And now we know what area that we are after, what area that we need to determine. The next step is we are fully aware that in order to get the area under the curve, our normal table will only give us the area from minus infinity to the z value or whatever the x value is required. So we need to keep that in mind. So now with this in mind, here is the sketch of the normal distribution. Here is the value of x desired. Here is the area required. And we can now use the transformation z being x minus mu divided by sigma, where is x is 110, mu is 88, and sigma is 12. Using that, we have a value of z of 1.833. So now I can go to the standard normal curve. I can sketch that actually. And we know how it spans. It spans from about -3 all the way to 3. And the center is 0. And if z is 1.833, then it's somewhere in here. And now I'm after this area here. But the normal table will not give us this area. Instead, it will give us this area. So if I go here and look at the normal table, I can see that at 1.83, which is this one here, 1.8, 3 is direction, I will have an area of 0.9664. And what does that mean? It means this entire area from minus infinity to z is 0.9664. But that's not the area that I'm after. I'm after the shaded area here. But I also know that the entire area under the curve is 1. So 1 minus this area will give me the shaded area. Or in percentage, this is about 96.6%. So what we are talking about here is about 3.4% or 0.0336. Okay? So we have a 3.4% of people that have above average or better IQ according to the parameters we have. So in summary, we start out with a sketch in the normal distribution. We then identify the x values of interest. We then convert the x values into a z value, and then we obtained the area under the curve from the normal table, and these are the steps that we discussed earlier. Now, if you want to get the percent of people that have an IQ from 90 to 109, we will do the same steps. We have the normal curve, as you can see here. We will identify the x values. Here is the 90 and here is the 109, meaning that we need the area in the middle or the shaded area here. Then we need to convert these x values into z values. And here is the conversion using the equation we discussed before, the z-score, x minus mu divided by sigma. And now this becomes a normal problem that we solved it before of finding the area or the shaded area under the curve. Here is another example. A sawmill pays workers by the quantity of garments they make. The average annual pay per worker is 18,000 and the standard deviation is 4,000. So that leads us directly to sketching the normal distribution with a mean value of 18,000 and the standard deviation of 4,000. Now the question is, if we draw a worker randomly, then find the probability that the worker selected randomly earns between 13,000 and 20,000. Now these are two x values that we have to identify on the standard, on the normal curve. So here they are, 13,000 and 20,000. And the question is about the probability of a worker selected randomly earning any value in this range, which is expressed by the area under the curve, because the area under the curve is in essence a probability. Keep in mind that the normal distribution is a probability distribution. So again, as we did before, we will take these two values, convert them into z values. At 13,000, x minus mu divided by sigma is 13,000 minus 18, which is the mean, divided by sigma, which is the 4,000. That will give us minus 1.25. And keep in mind, the sign is very important. You cannot ignore the negative sign here. Otherwise, that will alter the answer. At x equal 20,000, we have a positive value of z because it's 20 minus the mean value of 18,000 divided by the standard deviation, and that gives us the z value. And now that we have the two z values, we can sketch the standard normal distribution, and now we have a problem that we dealt with before many times. We have the minus 125 to the left side of the curve, and we have the plus 0.5 to the right side of the curve, and we need the shaded area here. And how we do that? We go to the normal table, and at 0.5 we can find the area to the left, the entire area from minus infinity to z equal 0.5, which is 0.6915. This is the entire area. And at minus 1.25 we can go to the minus value table, which is 1.25, and that will give us an area of 0.1056, which is the small area here. And if we can subtract the big yellow area from the green area, that will give us the area desired. As you can see here, A at 0.5 minus A at minus 1.25, that will give us 0.5859 or a percent to 58.6%. So if we draw a sample or a worker randomly, the chance that this worker will be earning from 13,000 to 20,000 will be 0.58 or 58.6%. Another way to express that is about 58.6% of the workers are likely to earn from the two values, the 13,000 to the 20,000 specified in the problem. Here is another example. Suppose a technical institute was interested in the SAT math section with the hope to get students from the top 25%. Now we need to pay attention to this problem because it is the reverse problem. Meaning we're going to be given the area and we are looking for the z value. So in the state this institute is located, the average score in the SAT math section was 550 and the standard deviation was 30. And the question is, what would be the score this institute would accept? Now keep in mind that this institute will take the top 25%. And once again, we sketch the normal distribution, as you can see here, with well-identified mean value. Standard deviation is identified, and once we start doing that, then we start looking at the top 25%. Now how are we going to do that? Here is a standard normal table, and here is a rough sketch of the 25% to the right, because that's the top 25%, meaning the area to the left is 75%. Now we have an area and we need the corresponding z value. We go to the table and we look for what area we're going to look at. We are not going to look for the right area because that's not the area given by the table. We're going to look at the left area, which is the 0.75. Now looking at this area, it's somewhere in here. It's not exactly 0.75, but it is 0.7486, as close as it can get to the 0.75. At this area, our z value is 0.67, as you can see here, 0.6 from the first column and 0.7 from the first row. So our z value is 0.670. Now that doesn't finish the problem, because we still need to take that z value and convert it back to an actual score. And the way we do that is by using the z formula. What we have here is z equal 0.607. Now z is equal x minus mu divided by sigma. Now x minus mu divided by 30 equal 0.67. And that, by solving this simple equation, we can get the x value of 570.1. What does that mean? It means this institute, taking the top 25%, will have to take any score at 570 or more in order to satisfy their acceptance criteria. What we covered here is actually few applications that gives us a good idea about how we can use the normal distribution to solve real examples and reveal important information. In the next session, we will see how we can use Excel, Microsoft Excel, to perform some of these calculations easily and efficiently.